Welcome everyone! Today we're going to learn about autoencoders and how we can implement them in PyTorch. Autoencoders are really cool and the mechanism is actually pretty simple. In this case, we deal with an input image and we want to encode it to get a low-dimensional embedding of the image. And after that, we want to decode it again and reconstruct the original image as good as possible. So that's the whole mechanism behind it. So we deal with the original image, get an encoded image, and reconstruct the original image again. A very cool possible application for this is, for example, video compression, where we want to send over the images over the network from one end to the other end. So instead of sending the whole image, we could simply send the encoded data only, and on the other side, we then have the decoder stored and can decode the image again. This would save a lot of cost and could be much faster, and I think this is pretty cool. So how do we encode and decode the image? For both operations, we can simply use a feed-forward neural net, or when we deal with images, we often use a convolutional neural net, which usually performs better, and later I will show you how to code both versions in PyTorch. When we speak about such a model, we call this a generative model, because here, instead of doing a classification at the end, we want to generate images based on the encoding. So in order to train our model, we need a loss function that we want to optimize. We want our reconstructed image as close as possible to the original one, so all pixel values should be almost the same. So our loss function is simply the mean squared error, which calculates the difference between all intensity values, sums over all pixels, and then calculates the mean value. Now here's a little trick in order to understand the whole process better. Instead of thinking about all transformations as operations in one way, we can think of this as a circular or forth and back operation. We encode in one direction and then we want to go in the opposite direction and decode it again to get the original image. So for each transformation we apply in the encoder, we want to apply the inverse of this operation in the decoder. For example, if we apply a linear layer that reduces the size, the reverse operation is also a linear layer that increases the size again. Now for CNNs, this is a little bit trickier. Here we apply convolutional layers. So the inverse is actually called a transpose convolution. PyTorch has this layer already included for us, so we can simply use the nn.conf transpose 2D layer. The only tricky thing with this is to determine the correct input and output shapes, but I will show you how to do this later. Alright, so that's everything we need to understand autoencoders. Now we can jump to the code. And if you enjoy this content, then I would be very happy if you hit the like button and subscribe to the channel. Alright, so here we are in a Jupyter notebook and we already have all the imports that we need. So we have Torch, we have Torch NN, Torch Optim, we have datasets and transforms from the Torch Vision module, and we have matplotlib to plot the data later. And then the first thing we want to do is load the MNIST data, and for this we use a Dataloader. And if you don't know how a Dataloader works, then I will link a tutorial where I explain this here. So we define a data loader and we can give it a batch size here. And we also define the data set. So this is included in PyTorch and we get this by saying datasets.mnist. And this will download the data and store it here in the data folder. And we also can apply a transform here, and in this case we simply apply a to-tensor transform. So this will transform the images to a PyTorch tensor. And I pulled this out here because this is actually important for our model later. So later I also want to show you what we have to consider when we use a different transform here. So we will get to this later. But for now, what we want to keep in mind is how our data looks like. So what values do our MNIST images have? So let's actually run this and let's inspect the first images or the first batch. So we get the first batch by creating a iterator object like so. We say data iter and then we call iter with our data loader, and then we pull out the first images and labels by calling data iter.next. And then we want to print the minimum and the maximum value, and we get this with torch.min of our images and also torch.max of our images. So let's run this. And then we see the values range from 0 to 1. So this will be important for our model later. And this might change if we also change the transforms here. So we will learn how to do this later. So with this in mind, that the values are between 0 and 1, we can create our Autoencoder class. So let's create a class and let's call this Autoencoder, and this is our model. So we have to inherit from nn.module. And if you don't know how to do this, then I will link another tutorial here where I explain how you create your PyTorch classes. So the first thing we want to implement is the init function, and this only gets self. And then we also want to implement the forward pass, and this gets self and x. So for now we only say pass. And in the first example, I want to show you a simple feed-forward neural net with linear layers and a few hidden layers. And here what we want to do is we want to repeatedly reduce the size. So in the beginning, our images have the size n and then by 784. So this is 28 by 28 because this is how many pixels the images have in this data set. And n is our batch size. So now we want to reduce this with a few linear layers. And a good way to structure your code in an autoencoder is to use a sequential model. So first we create a encoder, and this is a nn.sequential model. And now here we want to repeatedly apply linear layers. So let's create a first linear layers, and the input size is 28 by 28. So this is 784. And the output size, here we can play around with different sizes. So as first output size, I want to use 128. So what this is doing is this will reduce the size from n by 784. We'll reduce it to n by 128. After this, we also want to apply a activation function. So here we use nn.relu, the most popular one. And let's move the comment up here again. And now we want to do this multiple times. So now we want to create another linear layer, and this time our input is 128, and as output we can choose a different smaller size. So here I use 64. And then again we want to apply the relu activation, and then let's do this a couple more times. So let's actually copy and paste this. So we create another linear layer. And here we use 64, and as output let's use 12. Then again we have the relu, and now we create one last linear layer, so nn.linear, and here we use 12, and as output size let's use 3. And then as the last layer, here we don't need an activation function, so let's remove this again. So now this is our sequential model for the encoder, and the final output size here is n by 3. So this will drastically reduce the size of our input images from this size to only this size, and then later we are able to almost perfectly reconstruct this again. So this is really great. So yeah, this is our encoder. And now we want to do the same thing in the opposite direction. So let's copy this actually and say this is our self.decoder. So here we want to go in the opposite direction. So here we want to go from n by 3 all the way again until n by 784. So let's remove the comment here. And so now we want to look at all the linear layers and switch the sizes. So here the input size is 3 and the output size is 12. Then here we have 12 and 64. Here we have 64 and then as output size 128. And here we have 128 and as output size 28 times 28. And now we also here we apply ReLU activation functions in between. And now for the last layer, this is actually important. So here we have to apply another activation function. So let's go back to our data set and have a look at this. So we know that our images have values between 0 and 1. So we need an activation function that puts the values in exactly this range. So in this case, the $1 million question is, which activation function do we need to get outputs between 0 and 1? So this is the sigmoid function. So we get this by saying nn.sigmoid. So this is what we need as last layer. So keep this in mind. So now we have our encoder and our decoder, and in the forward pass we simply apply both of them. So we say encoded equals self.encoder, and this gets X. And then we get the decoded again by calling self.decoder, and this gets the encoded as input. And then we simply return the decoded image again. And yeah, this is all we need for our encoder class. So as a note here, keep the last layer in mind. For example, let's say our input images are in the range -1 and +1. Then we don't need the sigmoid here. So in this case, we, for example, want to apply the tonH function. And this might actually very easily happen if you apply a normalization here. So let me quickly show you how to do this, and that's why I pulled this out. So let's say our transform is transforms dot and then compose, and here we can give it a list. So the first one is again the tensor transform. And then we also apply transforms dot normalize, and here we want to use 0.5 for the first dimension, and for the other dimension we want to use 0.5 as well. So now if we comment this out, so let's actually run this and then also run this again and have a look at torch min and max. Then we see we get the range from -1 to +1. So that's why we always want to analyze our data first and want to know what are the ranges. And then here we might use, for example, the tonH. So keep this in mind. So now I will comment this out again, and we simply use the tensor transform. And now we have our images in the range 0 and 1 again. So now here we created our encoder. So now we actually want to set this up. So we create a model and say this is our encoder. Then we also need a criterion. And I already told you that this is simply the mean squared error loss. So we get this by saying nn.mse loss, and we also need a optimizer. So optimizer equals torch.optim, and here let's use the Atom optimizer, and we want to optimize the parameters of our model. And we also need a learning rate. So here let's use 1e minus 3, so 0.001. And also, if you want to, you can give this a weight decay. So weight underscore decay equals, and let's use 1e minus 5. So you can play around with these numbers and see which performs better. So let's run this cell, and now we get an error, and this is because in our init function, of course, we have to call super dot underscore init and initialize the superclass. So I always forget this when I record tutorials. So let's run this again, and let's run this again, and now this works. And now we do the training. So for this, I simply copy paste this here. So if you don't know how the training loop works, then I will link another tutorial here where I explain this. So basically we define the number of epochs, and then here I will set this to 10. Because this might take a few minutes to train if you don't have a GPU. So you can, of course, increase the size if you want to have more accurate values. Then we create a list to store the outputs. Then we iterate over the epochs. And then we also iterate over our data loader. And now here we want to reshape the images in our first example, because the images are in the shape 28,28, and we want to have this in size 784. So that's why we apply this. Then we call the model and get the reconstructed image. Then we call the criterion with the reconstructed image and the original image and calculate the mean squared error. And then we have to be careful to always zero our gradients and then call loss backward and an optimizer step. And then we also want to print the epoch and the loss after each epoch. And we want to store the epoch, the image, and the reconstructed image in the outputs list. So let's run this. All right, so training is done and our loss slowly decreased. So it's still not that low, but maybe you might want to increase the number of epochs. But it's working, and let's actually have a look at how the reconstructed images look like. So let me copy and paste a simple function here that will plot the images. So we will plot the images every fourth epoch and create a figure. And then we get the images and the reconstructed images from the outputs array that we stored. And this is a torch tensor, so we want to call detach and then convert it to a NumPy array here for plotting. And then we iterate over the images and plot the first 9 images. And here we want to be careful. So here again, we want to apply the reshaping again in the reverse direction. So here we went from 28,28 to 28 times 28. And here we want to go in do the opposite. So we do 28,28. And then we simply plot this. So here our data has to be in this format. So let's run this. And we see, so this is after the first epoch, and we can almost assume the correct number, but it's very blurred. And then it's getting better after the next 4 epochs. And I think this is after 8 epochs. So then we see this image, and we see that the result is still a little bit blurred, but it's actually pretty good. So we can detect which number this is. And I think this is pretty good for a simple linear layer that reduces the size to only 3 output layers. So I think this is pretty cool. Yeah, so this is the first example I want to show you, and now we want to use a convolutional neural network and see if we can improve the performance even more with this. So let's run this again and create a new cell, and then let's actually copy and paste this class and put it down here. And for the first autoencoder, let's rename this to Autoencoder_linear. And this will be our CNN autoencoder. So here we do the same thing. And now the first we want to do is, now here we actually put them in as 28 by 28. So in our training function, training loop, we can remove this reshaping, and also later for plotting we can remove this as well. So let's do this first. And yeah, so now we can continue here. So now instead of linear layers, what we want to have here is convolutional 2D layers. So here we can say nn.conv and then 2D. And here we have to give it input channel and output channel. So this is 1. And then you can play around with this size. So let's use 16 as the first number of output channels. And then we also have to give it a kernel size. So here we use 3. Then we can give it a stride. So this is 2. And let's use a padding equals 1. So this is our first convolutional layer. And then as well here we want to apply ReLU activation functions. Then let's create another convolution, then again the ReLU, and then let's use another convolution, and actually let's get rid of those here. So we only want to do 3 passes. And now let's simplify this a little bit and get rid of this. So now it gets a little bit tricky because now you have to be careful to get the correct shapes and the correct input and output channels. So again, if you don't know how these convolutions work, then I will link the tutorial about the CNNs where I explain this. So actually, let's inspect the input and output size. So the input for this is n by 1 by 28 by 28. So this is why our first input size is 1. And then after that we get 16, and for the size we get 14 by 14. So we reduced the size of our images by 50%. And then for our next one, as the input size, we have to get the output channel size of the previous one. So this is 16. And then here we can actually increase this and use 32. And we will keep the rest. And then again, let's have a look how this will look like. So this will be n by 32 by 7 by 7. So again, we reduced this in half. And then again, we use a ReLU, and then again a convolutional, and this will have 16. Let's actually increase this again. So 64. So here we have 64 output channels, and then here we want to use, let's use 7. So we have 1 by 1 as the output size of our image. So basically only 1 pixel, but 64 channels. So we increased the channels, but we reduced the size of the image. So now this has far more parameters than this size. So this is our encoded version. And now we want to go in the backwards direction with the conv transpose 2D layers that I mentioned. So here let's copy and paste this to know with what size we are working here. So now we apply the nn.conv transpose 2D. And now here we again have to switch the sizes. And here I made a mistake through copy and paste. So here this input size must be the output size of this one. So here we have to say 32 and then 64 and 7. And here we do the opposite. So we have 64 input channels and 32 output channels. And the kernel size is 7. So this will give us the size n by 32 by 7 by 7. So like we have here. So this is correct. Then again, we use a ReLU. And now let's use another conv 2D, conv transpose 2D. And here we switch this convolutional layer. So here we have 32 as the input, and 16 as the output and a kernel size of 3. And now if you run this, then this will actually give you a size of n by 16 by 13 by 13. And what we want, we have 16 by 14 by 14, so we need +1. So this is a little bit tricky, so I recommend to play around with these ones and have a look at what they generate. And now in order to compensate this, we can give it a parameter. And here, let's use the exact same stride and padding that we have here. Stride equals 2 and padding equals 1. And then we can say output padding equals 1. So this will put zeros in it so that you get 14 by 14 now. So yeah, this is a very important thing to know, to use the output padding parameter. And now again we use the relu function, and then we use another conf transpose to d. And here we have to revert this one. So as the input we use 16 and as the output we use 1. And then again, we have the same kernel size, the same stride, and the same padding. And now here will happen the same thing. So if we don't use this, then we get n by 1 by 27 by 27. So then again, we need the output padding, and then we get n by 1 by 28 by 28. And then we don't need these anymore. And again, as the last layer, we want to have the sigmoid, so the same as before. And now this is no longer correct. So yeah, this is how we implement a autoencoder with convolutions. So we need the convolutions, and then in our decoder we use conf transpose to d. And be aware that you use the correct shapes and also maybe use an output padding if necessary. So let's run this. And here I actually want to mention one more thing. So a lot of times in convolutional neural networks, you use the maxpool2d function. So nn.maxpool2d. This will essentially reduce the size, and to revert this, there is also a function that is called nn.maxunpool2d. So this is what you might want to use in the decoder then, but you don't need to do this. You can also, for example, play around with different strides and paddings and kernel sizes. The only thing you want to make sure is that at the very end you get the same output shape as you had in the beginning. So yeah, keep that in mind. And now let's run this. And now let's create our new model with the convolutional autoencoder. So let's run this again. And then again, let's run the training and see how this performs. All right, so our training is done, and again our loss decreased, and now this time it's much better than before. So I guess before we had 0.03 something, and here we have 0.00 something. So this is much better. So yeah, we can see that our CNNs usually perform much better than a simple feed-forward neural net with linear layers. So let's actually run our plotting loop again, and let's plot some example reconstructions. So we can see that after the first epoch, it's a little bit blurred, but it's already very good. And then this is after the fourth and after the eighth epoch. And we can see that already here, the reconstruction is pretty good. So yeah, I think it's almost the same image. So yeah, this is really cool, and this worked. So yeah, this is how you implement a autoencoder with PyTorch, and I really hope that you enjoyed this tutorial. And if you want to have a small exercise, then I can give you the exercise to apply the maxpool2d and the unpooling that I mentioned. And you can also try to inspect the encoded data and see if this can actually be plotted and how this looks like. So yeah, this is something you can try out for yourself. And then I hope to see you in the next video. Bye.